Hello, cloud gurus. Kubernetes has its own terminology. So, if you want to use Kubernetes, there are a few terms that you first need to be aware of. Now, I promise that this is the last bit of theory before we jump in and start using Kubernetes. And even in this lesson, I'm going to periodically jump out to the command line into the lab and show you how these terms are used in the real world of Kubernetes, and I encourage you to follow along when I do so. We've got a lot of cool new Kubernetes terms to learn. Let's get started. Cloud native applications running in microservices architectures are popular topics because they give businesses greater flexibility, greater scalability, greater availability, and the agility that the company needs. They also provide a lot of flexibility to developers. But what exactly are microservices applications, and what do they have to do with Kubernetes? If we step back and talk about traditional applications are very monolithic, where they consume a ton of resources to run their own operating system, authentication, web server, middleware, database, and analysis, perhaps, all on the same virtual machine or physical server. These applications are difficult to upgrade, they're difficult to scale, they're difficult to make highly available, and these are all things that the business needs. For greater agility, efficiency, and scalability, companies are moving to these microservices architectures. So the same type of monolithic traditional application can be broken up into this microservices application, where those same services are being run, but in this case, they might be run inside individual containers. For example, authentication, web server, middleware, database, and analysis can all be run inside individual containers with different resource allocations or multiple containers. And that way you can easily scale up or down individual services. You can also upgrade individual services or replace individual services. However, as you might guess, this also increases complexity if it's done manually. It's Kubernetes that makes these microservices architectures and applications possible and enables the next generation of cloud-native application. So for the future, both the business and developers want these microservices cloud-native applications, but they need container orchestration to make them possible. So exactly what does container orchestration do? Well, Kubernetes is a container orchestrator, and it optimally runs your workloads. It provides access to needed storage and networking resources. It ensures the applications run with the business intent. That means that I can say, I want 10 database servers, 25 web front-end servers, and 13 analysis servers all running inside containers. And Kubernetes will ensure that that is always the case. If one of those services fails, it will automatically restart another service to ensure that the application is always configured and running with the business intent. And by doing so, it provides greater efficiency for the developer and the administrator, high availability, and load balancing. For example, let's say we have a 3-node Kubernetes cluster. Each of these nodes is running 2 pods which contain a single container each, providing a capacity of 6 total containers running the business application. And let's say that one of these nodes fails. It has a physical failure, the power is off, it crashes, whatever it might be. Kubernetes will realize that the business intent of having 6 pods running at all times is not being met, and it will automatically restart the failed pods on the remaining nodes. So again, container orchestration provides high availability, load balancing, because inbound connections can be distributed automatically across all the nodes that are running the workload, resource management, and desired state configuration through a declarative model, meaning you define exactly for Kubernetes what you want to be running at all times, and it will ensure that it is indeed running. The next term I want to talk about is a cluster. In the world of Kubernetes, a cluster is a collection of nodes, also known as hosts, storage, and network resources that are used to run your workloads. You may have one or multiple clusters, and every cluster will have at least one Kubernetes master. If we take a look at our diagram, this is the typical cluster here. You have a master node, which we'll talk about more in just a minute, and then a worker node, or just a node as it's called in Kubernetes. And in production environments, you would probably have multiple master nodes and many worker nodes that actually run your workloads. Here at the command line, if I type kubectl get nodes, you can see we have a single node in this cluster. The name of that node is Minikube, its status is ready, and it is a master node. We said that the Kubernetes cluster is made up of a master node and then just a node or a worker node. It's the master node that's the control plane of Kubernetes, and it's made up of a number of different components, such as the API server, the etcd key value store to store all the stateful Kubernetes data, the Kubernetes scheduler, the controller manager, and the cloud controller manager. The role of the Kubernetes master is to schedule workloads in the form of pods and handle all events. Again, it's the control plane. It's the manager of the entire Kubernetes cluster. It could be a physical host or it could be a virtual machine. And it could be running on premises in your own data center or it could be running in a cloud instance. Again, the most important components of a Kubernetes master are the API server, which is constantly talking to the worker nodes in the cluster, as well as the kubectl command line tool and other tools that Kubernetes is integrated with. The scheduler, which schedules new workloads on the nodes in the cluster, the controller manager, which ensures that the workloads that are being controlled are running as they should, and then the etcd database to store all the stateful data that's relevant to keeping these workloads running. If we jump to the command line and run kubectl get pods, and then use -- all namespaces, and we'll talk about namespaces more in just a minute, you can see that we have a number of pods running, and each one of these has a container inside, but you should see here the different services that make up the Kubernetes master. There's etcd, the API server, the controller manager, the scheduler, and a number of other optional Kubernetes master services. In Kubernetes, we have a number of different namespaces. Namespaces are a logical abstraction of the Kubernetes cluster that allows you to support multiple virtual clusters. And you use resource quotas to manage the resources that are consumed in each of the namespaces. There are 3 different default namespaces: the default namespace, kubesystem, and kubepublic. When you run a workload in Kubernetes, it's going to run in the default namespace by default. All of the control plane services that make up the master are run by default in the kubesystem namespace. If we take a look at a diagram, here we have a Kubernetes master and 3 nodes. Each node is running a number of pods, but if we wanted to, we could create a resource quota and allocate just certain pods to a specific namespace. Perhaps you have a group of developers who are developing a specific application. You want to make sure that they don't interfere with perhaps production applications that might be running in the default namespace, or vice versa. You can create multiple namespaces. You cannot nest namespaces, but they make a very convenient logical abstraction instead of you seeing every workload that's running across the entire Kubernetes cluster. For example, here at the command line, if we type kubectl get namespace, you can see all the namespaces that are configured on this Kubernetes cluster, including default, kubepublic, and kubesystem. And then we have nodes, and we've talked a little bit about nodes already, but nodes are controlled by the master. It's these nodes, or worker nodes as I like to call them, that are made up of a few components such as the kubelet, which is essentially a Kubernetes agent, so it can communicate and work with the master node via the API server, the kube proxy, which is a network proxy that runs on each node, and then the pods themselves, which are essentially wrappers around your containerized workloads. And it's important to note that in the past, nodes were called minions, a name that I like much better than simply node. So if you see any old documentation or content that refers to Kubernetes minions, just know that they're talking about nodes. A node is a single host, and it could be a physical host or a virtual machine, and it could also run either on premises in your data center or up in the cloud. If we look at our diagram here of the master with 3 nodes, you can see that's an example of a node running the kubelet, kube proxy, and in this case, 3 pods which contain our containerized workloads. Back here in the lab, if we type kubectl get nodes -o equals wide, we get some more details here. You can see, again, the name of this node is Minikube. Its status is ready. It's a master node, but we also get information on the Kubernetes version, in this case 1.16, and we can see the container runtime is Docker. And then the final term before we start our deployment of Kubernetes is pod. Now, a pod is the unit of work in Kubernetes. So a pod is what runs your applications. And those applications are the whole reason that you're running Kubernetes to begin with. Pods contain containers, and those containers contain your applications, whether it's a web server, a database server, or some analysis server. A pod can have one container or multiple containers, but typically administrators just run a single container inside a pod. All containers in a pod have the same IP and they can communicate with each other. And they also have access to the same shared storage. Pods are identified by a unique UUID. And if we take a look at our diagram here with our Kubernetes cluster, where we have our master node and 3 worker nodes, you can see on each of these worker nodes, that's where we're running our pods. Inside those pods are our containers, which contain our applications. And the typical microservices architecture would dictate that a single application for the business would be broken up across multiple pods and multiple containers, just like we talked about at the start of this lesson, where you might have multiple web server pods, multiple database server pods, a few authentication server pods, some logging server pods, and they're all orchestrated or distributed across the cluster thanks to Kubernetes. Back here in the lab, and I encourage you to follow along if you'd like, you can type kubectl get pods. And in this case, we haven't started any pods, right? We're not running any pods yet. However, that's in the default namespace, which is a term we talked about earlier. If we wanted to get all pods across all namespaces, we can use this command, which we ran earlier, get pods -- all namespaces. And you can see there we are actually running many pods in this Kubernetes cluster. However, these are all in the kube system or Kubernetes dashboard namespace. A little bit later in the course, we'll start up our first Kubernetes pod, and that pod will be running in the default namespace, which is where your pods are going to run, well, by default. And with that, we've reached the summary for this lesson. In this lesson, we learned a lot of different terminology as it pertains to Kubernetes. Specifically, we started off by talking about microservices applications, how monolithic applications more and more are being broken out into these microservices applications. And in order for those applications to be successful, they really need to be run in containers, and those containers need to be orchestrated. And that's the job of Kubernetes. We talked about how Kubernetes orchestrates those containers in clusters, and those clusters are controlled by master nodes. Now, you can logically segment your cluster into namespaces, and in fact, that's done by default with the kube system and the default namespace. From there, we learned how Kubernetes nodes are actually what run your containers, and how those containers are run inside the Kubernetes construct of the pod. Thanks for sticking with me all the way through this lesson on critical Kubernetes terminology. We're about to deploy Kubernetes, and it's going to be a lot of fun. I hope you'll join me in the next lesson.